a laser pointer, or even just, felt the warmth of the sun and wondered about the fundamental nature of light and energy. Today, we're plunging into a seemingly simple equation that utterly overturned our understanding of the universe. E equals h nu.
It looks so simple, doesn't it?
Mhm.
E, just 3 letters, an equal sign.
Huh.
But wow, it cracked open a door to a whole new reality.
It really, really did. We've pulled together quite a stack of sources for this deep dive: articles, research notes, things to help us really get a handle on this cornerstone of quantum theory.
Yeah, our mission today, I think, is to trace where it came from, figure out what each bit of this famous little formula actually means, and maybe most importantly, understand why it still matters so much.
Yeah.
How it influences everything from, the tiniest subatomic particles right up to the light from distant stars and even the tech you're probably using right now.
Okay, all right, let's unpack this. To really get why E was such a bombshell, we need to set the scene a bit. Let's go back to the late 19th century.
Right. This was a time when classical physics felt pretty much complete, didn't it?
Yeah, absolutely. You had Newton's laws for motion, Maxwell's equations nailing electricity and magnetism. They seem to explain everything you could observe, from apples falling to radio waves.
Incredibly successful. Classical physics painted this picture of a universe that was smooth, continuous, predictable, like clockwork. But there was this one nagging problem, a persistent little puzzle.
Right, this thing called black body radiation. Can you remind us what a black body is in physics terms?
Sure. So imagine an idealized object, perfect absorber. It absorbs all the light that hits it, nothing reflected. Then when you heat this thing up, it glows. It emits electromagnetic radiation, light, purely based on its temperature.
Yeah.
And it produces this unique spectrum, different colors, different intensities as you change that temperature.
Like a blacksmith heating metal, right. It goes red, then orange, then maybe yellow, white, hot.
Exactly like that. So scientists back then, late 1800s, they were carefully measuring the spectrum of light coming off these hot objects.
Okay, so they had the measurements. What did the existing physics, the classical physics, predict they should see?
Well, they applied the rules. They knew classical electromagnetism, thermodynamics, and they worked out a formula. The famous one is the Rayleigh-Jeans law. And this was supposed to describe the intensity of the light at all the different frequencies or wavelengths.
And how did that prediction match up with reality, with the experiments?
Well, it kind of worked okay at low frequencies. The long wavelengths like infrared or radio waves. Down there, the classical prediction and the experimental data lined up reasonably well.
What? I sense a but coming.
Oh yeah, a big one. As they looked at higher frequencies moving towards visible light, and especially into the ultraviolet part of the spectrum, the classical prediction just went completely off the rails.
Off the rails, how?
The Rayleigh-Jeans law predicted that the energy radiated would just keep going up and up and up as the frequency got higher, towards infinity, actually.
Infinite energy, that sounds bad. Like physically impossible.
It was. A catastrophe, you might say. It meant any hot object should be blasting out infinite amounts of energy, especially in the UV range and beyond. They literally called it the ultraviolet catastrophe.
Because experiments obviously didn't show infinite energy.
Not at all. Experiments clearly showed the intensity rose, peaked at a certain frequency depending on the temperature, and then dropped off again at higher frequencies. It didn't shoot up forever.
Okay, so this wasn't just a small error. This was a fundamental breakdown. Classical physics just couldn't explain this basic phenomenon.
Exactly. It was a huge sign that something was deeply wrong with their understanding of how energy and radiation work together.
And into this mess, this catastrophe, steps Max Planck around 1900.
Yep. He was trying pretty desperately, actually, to find some formula, any formula, that would just fit the experimental data for the black body spectrum.
Can he landed on something?
Radical.
Right, an idea that even he wasn't entirely comfortable with at first.
That's the story. To make his formula work, he had to make this completely wild assumption. He proposed that energy isn't continuous. It doesn't flow smoothly like water. Instead, he suggested energy is emitted and absorbed only in discrete, specific little packets, bundles. He called them quanta.
Energy comes in chunks. That's a massive leap from the smooth world of Newton and Maxwell.
Huge leap. And he introduced this relationship, E-high, to define the energy of one of these fundamental packets, these quanta, based on the frequency of the radiation.
E, the equation we're diving into. So how did this idea of quantization of energy packets fix the ultraviolet catastrophe?
Well, Planck imagined the radiation coming from tiny oscillators inside the material of the black body, sort of like tiny vibrating springs. And he made this crucial assumption These oscillators couldn't just vibrate with any amount of energy. Their energy was restricted, quantized. It had to be an integer multiple of a basic unit, zero energy, or high, or 2 or 3 key, and so on.
Okay, so no values in between, like 1.5 high.
Yeah. Exactly. Like climbing stairs, you can be on step 1 or step 2, but not step 1.5. Because it takes a certain minimum chunk of energy to excite an oscillator at a given frequency, and for very high frequencies, that chunk becomes quite large. So at a given temperature, it becomes much less probable, statistically, to gather enough energy to excite those very high-frequency oscillators.
Which means they don't radiate much energy at high frequencies.
Precisely. This inherent chunkiness choked off the energy contribution at the high-frequency end, preventing that climb towards infinite energy.
Okay, and to make the numbers fit the experimental curves perfectly, he had to introduce this new constant, this H, Planck's constant.
Yes. H is the constant of proportionality. It links the energy of that quantum packet directly to its frequency. And its value is, well, it's incredibly tiny, about 6.626 times 10 to the minus 34 joule seconds, minus 34.
Wow, okay. That smallness, that's the key to why we don't notice this quantization in everyday life, right? The energy steps are just far too small for us to perceive.
Exactly right. On our macroscopic scale, energy looks smooth and continuous because the individual steps, the quanta, are minuscule compared to the energies we usually deal with. It's a quantum effect, really only noticeable at the atomic scale.
And the result? Planck's formula, built on E high and quantization.
It perfectly described the observed blackbody spectrum across all frequencies, low, high, peak, everything. It completely solved the ultraviolet catastrophe. Nailed it.
It's still amazing, though, that story that Planck himself was uneasy about it. He saw it maybe more as a mathematical trick, a desperate act, he called it, not necessarily deep physics.
He did. He kind of hoped someone would find a way to explain it using classical ideas eventually. But the universe had other ideas, and Albert Einstein was about to run with this quantum concept.
Okay, before we get to Einstein, let's break down the equation itself a bit more. E. What's hiding in each letter?
All right. E is for energy. Specifically, it's the energy of one single quantum of electromagnetic radiation. This energy packet, this light quantum, later got a name we all know, the photon, though that name came a bit later, after Einstein's work really solidified the idea.
The photon. Okay, so E is the energy of one photon, the smallest possible bit of light energy for a specific frequency.
You got it, the irreducible packet. Then there's H, Planck's constant. We mentioned its tiny value. It's often called the quantum of action.
Quantum of action. What does that really signify? Sounds fundamental.
It is fundamental. It represents the basic granularity of nature at the quantum level. It tells us that physical processes involving things like energy and time, or momentum and position, have a sort of built-in minimum scale. They can't be infinitely subdivided or known with infinite precision together.
And it's universal, right? The same value everywhere for everything. And it's now so fundamental it's used in the official definition of the kilogram.
That's right. Since 2019, the SI unit definitions are based on fixing fundamental constants, and H is one of them. Its value is now exact by definition, which is used to define the kilogram. Kind of amazing that a constant from blackbody radiation now defines mass.
It really shows how interconnected physics is. Okay, last part. E, the Greek letter nu.
Nu stands for frequency, the number of wave oscillations per second, measured in Hertz. Hertz.
And frequency is linked to wavelength, isn't it? Through the speed of light.
Yep, the classic wave relationship. The speed of light, c equals wavelength times frequency e. So CLEs.
Which means we can rearrange that to get E, and if we substitute that into E...
You get the other very common form of the equation, E equals E.
Right, and I find that form really intuitive. It directly shows how energy relates to wavelengths.
Exactly. It makes the inverse relationship crystal clear. High energy E means short wavelength one. Think X-rays, gamma rays, lots of energy, tiny wavelengths. Low energy E means long wavelength, like radio waves or microwaves.
So the color of light, or its type on the electromagnetic spectrum, is directly tied to the energy carried by each of its photons. Red light photons have less energy than blue light photons.
Precisely. And sometimes people use a slightly different constant.
H bar.
Yeah, or H bar. That's just H divided by 2. It often shows up when you're dealing with angular frequency, usually written as O omega.
So you'll see EOO. It's mathematically convenient in a lot of quantum mechanics formulas, especially involving rotation or angular momentum. Same physics, just different units sometimes.
Okay, so Planck used E high and his constant H to fix this black body problem. But you said this was just the beginning. This is where things really took off.
Oh, absolutely. It wasn't just a fix. It was the spark. The very first step towards a completely new kind of Physics, quantum mechanics needed to describe the world of atoms and particles.
And a huge piece of early evidence confirming this wasn't just a fluke came from Albert Einstein in 1905, right, with the photoelectric effect. Yes, the photoelectric effect was another major headache for classical physics. The basic idea: you shine light on a metal surface and electrons pop out.
Okay, and classical physics, treating light as just a wave, had predictions about that.
It did. Classical wave theory said if you shine brighter light, higher intensity, the wave has more energy, so the electrons knocked out should have more energy too, more energetic kicks.
Makes sense, wave-wise. But what did experiments actually show?
Experiments showed something completely different. The maximum energy of the ejected electrons didn't depend on the light's brightness at all. It only depended on the light's frequency, its color.
Only frequency, not intensity. That's weird.
Very weird classically. And there was another thing. For each metal, there was a minimum threshold frequency. If the light's frequency was below that threshold, no electrons came out, no matter how bright you made the light. You could blast it, but if the frequency was too low, nothing happened.
Okay, another classical puzzle. How did Einstein use E-hide to solve this one?
Einstein took Planck's quantum idea really seriously. Maybe more seriously than Planck himself at that point. He didn't just say energy is emitted in quanta. He proposed that light itself is fundamentally composed of these energy packets, these photons, each carrying energy E high.
So light isn't just a wave, it's also like a stream of tiny energy particles, bullets of energy.
That was his radical proposal. He said when light hits the metal, an electron gets knocked out only if it absorbs the energy from one single photon. And that photon must have enough energy to overcome the work function, the energy holding the electron in the metal.
Ah, so if the frequency is too low, then high is too small. Not enough energy in one photon bullet to free an electron.
Exactly. No matter how many low-energy photons you fire at it, how bright the light is, no single electron gets enough energy in one hit to escape.
But if the frequency is high enough, above the threshold,
Then each photon does have enough energy to knock an electron out. And any extra energy from the photon beyond what's needed to escape becomes the electron's kinetic energy, its speed. Making the light brighter just means sending more photons per second, so more electrons get knocked out. But each one still only absorbs one photon and has the same maximum kinetic energy determined by that frequency.
that explains everything. The frequency dependence, the threshold. Brilliant.
Utterly brilliant. And that explanation of the photoelectric effect, relying entirely on the photon concept in E, is what won Einstein his Nobel Prize, actually, not relativity. It was powerful proof that Planck's quanta were real physical things.
And these two successes, black-body radiation sort of needing waves of quanta photoelectric effect, needing particle-like photons that really pushed the idea of wave-particle duality, didn't it?
It was definitely a huge early piece of that puzzle, this bizarre notion that light, and later matter too, can act like a wave in some situations and like a particle in others.
And the quantum idea kept spreading. It wasn't just light. Niels Bohr, 1913, he applied it to the atom itself.
Right. Bohr took the idea of quantization and applied it to the electrons orbiting the nucleus in an atom. He proposed that electrons couldn't just orbit at any distance or have any energy. They were restricted to specific discrete energy levels, quantized orbits.
Like planets only being allowed in certain orbits, but for electrons.
Sort of, yeah. Think of it like energy steps again. An electron could be on level 1 or level 2, but not in between.
And if an electron jumps from a higher level down to a lower one?
It has to release that extra energy. And how does it do that? By emitting a photon.
Ah. And the energy of that photon, let me guess.
Is exactly equal to the energy difference between the two levels the electron jumped between. Call that energy difference decay. And the frequency of the emitted light is given by EA cos high.
That's amazing. So that's why elements emit specific colors of light when you heat them up or pass electricity through them, those spectral lines.
Exactly. Each distinct line in an element's spectrum corresponds to an electron jumping between two specific allowed energy levels, releasing a photon with a very precise energy and frequency determined by high. It's like the atom's fingerprint or barcode.
Another huge mystery solved by quantization in E-high. This equation is just everywhere in the foundations of quantum theory. You even mentioned it pops up in Heisenberg's uncertainty principle.
It does, fundamentally. The uncertainty principle states there's a basic limit to how precisely we can simultaneously know certain pairs of properties of a particle, like position and momentum.
You can know where it is accurately or how fast it's going accurately, but not both perfectly at the same time.
That's the gist. And it's not just about our measurement tools being clumsy, it's an inherent property of quantum nature itself. And Planck's constant h, or rather h bar, sets the scale for this limit. The uncertainty in position times the uncertainty in momentum has to be greater than or equal to divided by 2.
So that tiny constant h is literally setting the fuzziness limit of reality.
In a way, yes. It dictates the fundamental granularity and the inherent limits on certainty in the quantum realm. It ties together the quantization of energy, the particle nature of light, atomic structure, and these fundamental uncertainties. It's incredibly profound.
Wow. Okay, so it's clearly fundamental physics, but you mentioned earlier it connects to technology we use every day. Let's talk about applications.
Right. This isn't just theory. E-high is actively used all over the place.
Like where? Give us some concrete examples.
Well, spectroscopy is a huge one. We touched on it with atoms. Scientists use instruments to very precisely measure the frequencies, and thus energies, via EI, of photons absorbed or emitted by materials.
And because different atoms and molecules have unique energy level structures.
They interact with unique sets of photon frequencies. That spectrum acts like a signature. So spectroscopy lets you identify what substances are present, what chemical bonds they have, their temperature, all sorts of things.
Used in chemistry labs, quality control?
Absolutely.
Yeah.
And also in things like pollution monitoring. Or think about astrophysics.
Analyzing starlight.
Exactly. Astronomers are basically doing spectroscopy on light that's traveled millions or billions of light years. EI lets them decode that light to figure out what stars and galaxies are made of, how hot they are, how fast they're moving.
Even the leftover heat from the Big Bang, the cosmic microwave background.
Yep, its spectrum is a near-perfect black-body curve. By finding the peak frequency of that curve, astronomers use Planck's law, which incorporates E, to measure its temperature incredibly accurately, about 2.7 Kelvin.
Okay, what about closer to home? Medicine.
Definitely. Think about X-rays. They are high-frequency, high-energy photons, large E. That high energy lets them pass through soft tissues, but get absorbed more by denser materials like bone, creating images. And gamma rays, even higher energy photons, are used in radiation therapy to target and destroy cancer cells, delivering lethal energy doses at a very specific location.
Lasers. You mentioned lasers earlier.
Lasers are a fantastic example. Laser stands for light amplification by stimulated emission of radiation. The core process involves getting atoms into an excited state, then stimulating them with a photon of just the right frequency to make them emit an identical photon, same E, same direction, same phase. This creates a cascade, an amplified beam of coherent light where all the photons have essentially the same energy.
EEDs, too. Solar panels.
Yes, all semiconductor devices dealing with light. LEDs work by electrons dropping across an energy gap in a semiconductor, releasing a photon with energy EI corresponding to the gap size, which determines the color. Solar cells do the reverse. Incoming photons with enough energy excite electrons across the gap, creating an electrical current. Designing these materials requires a deep understanding of these quantum energy levels and photon interactions.
It really seems like anywhere light and matter interact at that fundamental level, E-high is the key, even cutting-edge stuff like quantum computing.
Yep. In many approaches to quantum computing, you manipulate the state of quantum bits, or qubits. These qubits often have specific, quantized energy levels. Scientists use carefully timed pulses of electromagnetic radiation, like microwaves, where the frequency is chosen precisely using E-high to match the energy difference needed to flip the qubit from one state to another.
Okay. So Planck's initial idea, E-high, it was revolutionary, but it wasn't the complete picture, right? It was the start of a journey.
Exactly. It kicked open the door. But it took decades, and the work of many others, Schrödinger, Heisenberg, Dirac, Feynman, and so on, to develop the full mathematical machinery of quantum mechanics and then quantum field theory. These later theories provide a much richer, more detailed, and sometimes weirder description of the quantum world. But they all stand on the foundation that Planck laid with that simple relation and the concept of quantization.
It really is incredible, though, just thinking back, this one equation, E-high. It came from trying to solve a specific kind of obscure problem about how idealized objects glow when they get hot.
Black body radiation problem.
Yeah. And from that niche problem, it just exploded. It essentially marked the end of classical physics' absolute rule and launched the entire quantum era.
It really was the dividing line. By saying energy comes in packets, these quanta, and giving us the constant h to measure them, Planck gave us the fundamental tool needed to finally understand light, atoms, and how they interact. And as we've seen, that understanding underpins so much modern science and technology.
You can feel its presence everywhere, from astrophysics labs studying the early universe to the device you might be listening to this on right now.
And what always gets me is just how fundamental that constant h is. It's so incredibly tiny, almost unimaginably small, yet it seems to define the very texture of reality, the minimum grain size, if you like.
Yeah, that's a great way to put it, the granularity of reality itself.
Which maybe leaves us, and you listening, with a final thought to chew on.
Go.
If energy and action and these fundamental properties are inherently chunky or quantized at the very smallest scales, governed by this tiny constant h, what does that really tell us about the smooth, continuous world we seem to experience every day? How does that microscopic chunkiness build up into the macroscopic flow we perceive? It's still kind of mind-bending when you really think about it,